All right, if you're deep into machine learning, you've definitely come across the term SVM, support vector machine. But what is it, really? Well, today we're going to demystify this whole thing. Think of this as your exam-focused guide to really getting SVMs. Let's jump right in.
Okay, so take a look at this. You've got two groups of data points, right? The red ones and the yellow ones. Now, you could draw a bunch of different lines to split them up. I mean, you could draw one here, or even here. But here's the million-dollar question. Which one is the best one? The one that's going to work best for new data? That's the exact problem the support vector machine was born to solve.
So here's the plan. First, we'll cover the basics. What even is an SVM? Then we'll get into the secret sauce of how it finds that perfect line. It's all about something called the margin. From there, we'll look at what happens when a straight line just doesn't cut it, and that's where we'll meet the super clever kernel trick. And to finish it off, we'll wrap everything up into a neat little cheat sheet, perfect for when you're studying for that exam.
All right, let's kick things off. Section 1. What is an SVM?
So at its heart, an SVM is a type of supervised learning model. All that means is that you feed it data that's already labeled with the right answers. Its main mission in life? Classification. It's all about finding that perfect dividing line, which in the biz we call a hyperplane, to split our data into different groups.
Okay, so why should you care? Why is SVM such a big deal? Well, for one, it's a beast in what we call high-dimensional spaces. That's just a fancy way of saying your data has a ton of features, maybe hundreds of them. It's also really good at avoiding something called overfitting. You know, it doesn't just memorize the data you show it, it actually learns the underlying patterns, which is huge. And on top of all that, it's super flexible. It can handle problems that need a simple straight line and problems that are way more complicated.
All right, let's pop the hood and see how this thing actually works. How does it find that one perfect line? So the first thing an SVM needs is a decision boundary. Let's imagine we're trying to classify emails as either work or personal. And let's say we're just looking at two things: how many business words they have and how many emojis. Since we have two features, we can plot this on a 2D graph, and our boundary is just a straight line. Now that line has a formal name, a hyperplane. If we were in 3D, it'd be a flat plane. You get the idea.
Okay, you're going to see an equation here, but don't freak out about the math. The only thing you need to get is that this equation is the line. The W part, those are the weights, and they basically control the slope of the line. And the B, that's the bias, and it just shifts the whole line up or down. The entire job of the SVM is to figure out the perfect numbers for W and B to draw the best possible line.
So once the model has that equation locked in, classifying a new email is super easy. You just take the new email's features, like say it has one business word and two emojis, and you plug them into the formula. If the number that pops out is positive, maybe that's personal. If it's negative, then boom, it's a work email. Simple as that.
And here you have it, the final result. The SVM has found its optimal hyperplane, and it's doing a beautiful job of separating our data. Everything on one side is work, everything on the other is personal. It's clean, it's clear, and it just works.
Okay, but this brings us right back to where we started. How in the world did it pick this line out of all the possibilities? This is where the magic of SVM really happens.
I mean, think about it. There are basically an infinite number of lines you could draw to separate these two groups. So what's the secret? What makes one hyperplane better than all the others? How does the SVM know for sure that it's found the absolute best one?
The answer, in one word, is the margin. See, an SVM doesn't just want to draw any line. It wants to draw the line that creates the biggest possible buffer zone between the two classes. Think of it like a really wide street, or a safety zone. That zone is called the margin, and the SVM's entire goal is to make that margin as wide as it can possibly be.
Now, look closely at the data points that are right on the edge of that street. These guys are the VIPs of the whole data set. They're called the support vectors. And get this, the entire position and angle of that decision boundary depends only on these specific points. Seriously, you could delete all the other points and the line wouldn't budge. That's how important they are.
And here's why that matters so much for your exam. By maximizing that margin, the model becomes way more robust. A wider safety zone means the model's more confident. It's not getting thrown off by weird outliers. It's finding a boundary that's more likely to be true for all data, not just the stuff we trained it on. And that's exactly why SVMs are famous for being great at generalizing to new data.
Okay, so all of this is fantastic when your data can be split by a straight line. But, you know, the real world is messy. What happens when a simple straight line just isn't going to work?
Whoa, look at this. The data's all different now.
Suddenly, our personal emails are this little island in the middle of a sea of work emails. Go ahead, try to draw a straight line to separate them. You can't. It's impossible. This, my friends, is a nonlinear problem.
So, is SVM defeated? No way. This is where it pulls out its ace in the hole, its most famous and, honestly, most mind-blowing feature, something called the kernel trick.
The kernel trick is, frankly, genius. Here's a way to think about it. Imagine all those dots are marbles on a table. You can't slide a ruler between them to separate the colors. But what if you could flick the table and send the marbles flying into the air? For a split second, you could slice a sheet of paper between them. That's exactly what the kernel trick does, but with math. It takes our flat 2D data and projects it up into a higher dimension, like this 3D space.
And just look, suddenly, in 3D, the problem is easy again. A simple flat plane can cut right through the middle, separating the work and personal emails. Now for the final move. The model takes that flat plane and projects its shadow back down onto our original 2D graph. And what does that shadow look like? It's a perfect, curvy, nonlinear boundary that solves our impossible problem. So that magical math function that does the projecting, that's called a kernel. There are a few different types, but a super popular one you'll definitely see on exams is the RBF kernel, which stands for radial basis function. All you really need to know is that it's great at creating these circular or blob-shaped boundaries, which was perfect for our email problem.
Okay, I know that was a whirlwind, but we'd hit all the major points. Let's head into the home stretch and create a solid cheat sheet with everything you need to remember.
Okay, screenshot this if you need to. Here are the absolute must-knows. 1. Hyperplane. That's your decision boundary. 2. Margin. That's the safety zone the SVM tries to make as wide as possible. 3. Support vectors. Those are the crucial data points that actually define the margin and the hyperplane. And 4. The kernel trick. That's SVM's clever way of handling messy, nonlinear data.
And this final image really ties it all together. An SVM doesn't just give you a yes or no answer, it gives you confidence. A point way over here, deep in the blue zone, the models is super confident about that prediction. But a point right here, close to the boundary, the model's a lot less certain. And that ability to not just classify, but to understand the certainty of that classification, well, that's the real power of the support vector machine. It's all about finding that boundary with the biggest margin of safety, which is a pretty powerful idea, don't you think?